Great. To begin with, I would like to warn you that today's lecture is going to be a little bit boring. And this is because I have to tidy up some mess that I left behind. I am really sorry that my lecture is a little bit chaotic, but in order to somehow explain why it happens like this, let me tell you a very famous story about Alexander Grothendieck and Hajac. Hajac is one of the most famous, best institutes of mathematics in the world. And Alexander Grothendieck, the father of algebraic geometry, worked there. And once upon a time, there was a visitor and he complained, look, why in this institute, the library is so poor? Even at an average university, the mathematics library is much better. I can get many more books. And then Grothendieck answered, well, you see, here we don't read books, we write them. So let me answer in the same spirit. I'm not teaching you from a book. I'm writing a book teaching you. So as you can imagine, I have to go back, try to improve, try to make it consistent. But the upshot is that we are proving theorems much stronger and much better than you can find in the literature, at least if you search not long enough. So here you go. For starters, let me explain that I decided to call this set of all paths that are not vertices and that are not subpaths of a loop, let me call them the Jacobson subset, because it appears all over the place and it's really annoying all the time to say P is not the vertex and not the subpath of a loop. It's just the Jacobson set, all right? So that's the first thing. Next, I'd like to make sure that the end of the proof from the previous lecture is crystal clear. Remember, we finished by saying that, well, we basically finished the proof by my argument was a little bit chaotic, so I'd like to straighten it up and make sure that everything is crystal clear. So remember, we had a sum, here it is, which all of this had to vanish, okay? And we have two sets over which we sum, F7, and we have established that F7 is made out of loops based at S of A. And we also established that F9 contains at least one loop based at S of A, all right? And here we have the sum over the product of these two sets, okay? And then we chose a longest loop in F7 and the longest loop in F9. We called it C and D, all right? So this way it's obvious that if you take chi Q, chi C, and chi D, these loops compose, you will have chi C D, and this will be a non-vanishing term, okay? So this is where we ended up last time. Let me try to highlight it. Yep, here we go. Okay, so I have CD, which is a loop based at SA, that is longer than any loop based at SA, from F7 or F9, of course, because these loops are of positive length. And this term is non-zero. So the only way it can cancel, so that we remember that these are elements, chi's labeled by loops are elements of a canonical basis. So any subsets of such elements are linear independent. So if we are to get zero as required, and remember that by assumption alpha C and alpha D are non-zero and there are no zero divisors in the field, so therefore we get that this term alpha C alpha D chi C D is not zero, so it has to cancel with something else, and it can cancel only with another term which is also proportional to chi C D. Okay, and it cannot come from the sum over F9, it cannot come from the sum over F7, but we still have to entertain the possibility that it comes from this last sum, last of the three sums, the rightmost sum. Okay, so let's assume that this is possible. I'll try to unhighlight it. Yes, I highlight this. And now let's go here. So suppose we have other, or in principle, different two paths, C prime from F7 and D prime from F9, such that they compose to the same loop CD, okay? But now note that because C prime is a loop based at SA, and C prime D prime must be a loop based at SA, then also D prime must be a loop based at SA. Right? Otherwise, if C prime were a path, then D prime could also be a path, and they could compose to a loop based at SA. But because C prime is a loop based at SA, and the composition must be a loop based at SA, then we conclude that D prime actually must be also a loop based at SA. All right? Now, next, remember that C and D are longest loops in F7 and F9 respectively. So therefore, we can conclude happily that, and this is very important, that the length of C is the length of C prime, and the length of D is the length of D prime. Well, obviously, C prime cannot be longer than C, because C is a longest loop, and D prime cannot be longer than D, again, because D is a longest loop. So consequently, they can only be shorter or equal. Either we're shorter than C prime, D prime would be shorter than CD. So they actually have to be of the same length as C and D. But remembering that they are of the same length, well, we are home and dry, because now we can conclude. Now we can conclude that CD equal C prime D prime implies C equals to C prime and D equal to D prime. That's because they have the same lengths, okay? And therefore, the term proportional to chi CD appears in the rightmost sum only once, so it cannot cancel, which yields the desired contradiction. I mean, that sum, which is still highlighted here, cannot possibly be zero, okay? And then remember the conclusion as before. We have that, therefore, our assumption that the three were non-empty was false, and so F3 must be actually empty, and F3 being empty basically means that the Jacobson radical of KE is inside the span of chi p's with P running the Jacobson subset. You see how handy it is? I can call now the JE Jacobson subset. By the way, I changed the notation from J to JE because somehow canonically associated with every graph. And we are done. So this ends the proof of a theorem, which we did last time. And if you have any questions concerning this proof, it's time to ask them now. Are there any questions? Nope. Okay, so I stop sharing that screen and I start sharing my whiteboard. And now we continue. I want to draw a very nice corollary from this theorem. It's really elementary, although complete proof takes about half a page in LaTeX. But before I write this corollary, remember that by the property which we proved in one of the lemmas, that's just one lemma, within the lemma in the theorem, we know that if we take FPE and multiplied either from the left by the Jacobson subset or from the right by the Jacobson subset, we necessarily end up inside the Jacobson subset. So because of this property, we can actually say that this span, linear span of chi p's with P running the Jacobson subset can be viewed as the ideal generated by all the edges that are in the Jacobson subset. So I write them E belongs to E1 intersected with JE. Okay, and this is a slightly nicer way to put it, because when I say that this is an ideal generated by some edges, then it's a little bit more handy. But in particular, this leads this observation, this elementary observation leads us to the following corollary of the theorem we just discussed. All right. So as in the theorem, let E be a graph with finitely many edges, and let EJ, so I have JE and EJ. EJ is also canonically given for, we can call it the Jacobson subgraph if you want. Let EJ be its subgraph, obtained by removing from the graph E all edges that belong to the Jacobson subset. Okay, so in other words, EJ1 is equal to E1 less JE, and EJ0 is equal to E0. Okay, so this is our new subgraph. It's obviously a subgraph because we just take a subset in the set of edges, and we do not change the set of vertices. So obviously the restrictions of the source and the target maps exist. Okay, so clearly EJ is a subgraph. And now we have a very nice claim. Then, yeah, but I cannot write with an eraser. Then if you take the quotient of our path algebra by its Jacobson radical, lo and behold, this is again a path algebra. In fact, this is the path algebra of this new subgraph. Okay. Well, they are isomorphic naturally as algebras. Now let's prove it. And again, my apologies that the proof is going to be very boring. No fireworks here, but this is a regular lecture course, so by law, I should check all the details. The advantage of teaching from home is that I can drink my coffee. Okay, great. Now, proof. Observe first that we clearly have that if P is not in the Jacobson subset, then it follows that P belongs to the set of finite paths generated by the subgraph. Sorry, not, this should be crossed out. Okay, oops, what happened? I touched something without intending to do it. Okay, oof, my writing didn't vanish. Yeah, I mean, touch screens are nice, but sometimes you touch it unwillingly, and then it does something you do not wish it to do. That's exactly what just happened. I have to tidy up the mess on my screen. Okay. Erase some spurious marks. So P not in the Jacobson subset. Well, why is it the case? What does it mean not to be in the Jacobson subset? It means that P is either a vertex, and if P is a vertex and the set of vertices in EJ is the same as the set of vertices in E, then of course P is an FP and if P is a subset of a loop, it's a positive length path that is a subset of a loop, and then obviously each of edges building up this path is a subset of a loop. So it is built up from the graph which uses edges that are subsets of loops. Okay, because remember, we removed all edges that are not subsets of loops. So what remains are edges that are subsets of loops. Okay, so this implication is clear. And this allows us to conclude that the natural linear map let me call it pi. It goes from the path algebra KE. We take its basis element chi p, and we map it to, well, and here we have two possibilities. We map it to itself if P is not in the Jacobson subset, and we map it to 0 otherwise. Of course, now we are in the path algebra of EJ. Okay? So this linear map is well defined by this property that P not in JE implies P in FPEJ. Okay, because what we have to make sure of, that if P is not in EJ, then chi P is in this path algebra of EJ. So this means that P must be in FPEJ, but it is. Okay. But next, we can reverse this implication. So to see that this map is surjective, note the reversed implication namely P in FPEJ implies that P is not in JE, holds by another part of the same lemma, namely FPE not in JE squared. I have some junk which I have to clean, sorry. You see, I also touch my screen with my hand, not only with my pen, and this is why I have a spurious marks. Okay, that this is inside FPE less JE. Sorry, this should be not in JE. Right, I mean, P not in JE means P in FPE less JE. And why do we have this implication? Well, if I take any path built out of edges that are not subpaths of loops, then by induction, the composition of a path with an edge of a path which is not subpath of a loop with an edge which is not a subpath of a loop, this will give me something which is not a subpath of a loop exactly by this property, which I just recalled. So by induction, we will see that if you take edges that are not subpaths of a loop and you build any path out of them, a finite path out of them, then necessarily this will be a path which is not a subpath of a loop. So this means that it will not be in the Jacobson subset, and this means that our well-defined linear map is in fact surjective, right? Because if you look at how it is defined, I take any path P which is in FPEJ, right? So any basis element in the target space, and then I realize that this P is then is necessarily not in JE, so this chi P is in the image. Okay, so we have a well-defined surjective linear map, and now we use the theorem that we just proved, we see that the kernel, look, it's obvious that the kernel will be precisely, by the very definition, the kernel will be precisely chi-p's with p running the Jacobson subset. But we have just established in the theorem that this is precisely the Jacobson radical of Ke. So by the theorem, we conclude that the kernel of phi is the Jacobson radical of Ke. So if I take the quotient Ke by the Jacobson radical of Ke, it is isomorphic to the path algebra Kej, at least as a vector space. So it remains to prove that our beautiful surjective linear map is in fact an algebra homomorphism. Okay, so this is what we want to do now. So to end the proof, it suffices to show that phi is a homomorphism of unital algebras. So for starters, let us compute phi on the unit. And remember that the unit of a unital path algebra is just the sum over all vertices v of chi v. Well, but this is a linear map, so what we get will be the sum over v in E0 of pi. Well, let me write it down. Of pi of chi v. But E0 is definitely, but vertices are definitely not in the Jacobson subset. So by the definition of our map, pi of chi v is simply chi v. And now we can say that this v is running not the set of vertices in E, but the set of vertices in J. They are the same, so I can do it. So I just write it down as the sum over v's running E0 J, or EJ0, I should say. And here I have chi v. But this is one in the path algebra of EJ. So the map is unital. Okay. Next. And here, well, it's very boring. You just basically have to consider cases. And first case, let it be that I take two paths that do not compose. Okay. So first observe that since EJ is a subgraph of E, we have that paths that compose in EJ also compose in E. So you can conclude that if the end of a path P is not the beginning of the path Q, then pi of chi P chi Q is equal to 0, is equal to pi of chi P pi of chi Q. Well, why Well, oops, sorry, this is Q. Well, this is the left hand side is clearly 0 because chi p and times chi q is equal to 0. Pi of 0 is 0. On the other hand, we have to consider a bunch of options, namely either both P and Q are beyond the Jacobson subset. If they are both beyond the Jacobson subset, then pi of chi p is chi p and pi of chi q is chi q. And then we have chi p times chi q in the path algebra of EJ. But if these paths P and Q would compose in EJ, they would compose in E, but this is not the case. This is assumed. So they do not compose, so they multiply to 0. And otherwise, if at least one of these paths is in the Jacobson subset, then one of these pi's is equal to 0. 0 times anything is 0. So this is true. So at least for now, when we assume that we take arbitrary two paths that do not compose, then pi of chi p times chi q is equal to pi of chi p times pi of chi q. So this is, the homomorphism property. So now we take the other case and we assume now that these paths compose. So T of P is equal to S of Q. And for starters, let me assume that both of these paths are beyond the Jacobson subset. Then by this property from our lemma, that Fp E less Je squared is inside Fpe less Je. By this part of the lemma, we can conclude the following: pi of chi p chi q. Well, now they compose, so this is pi of chi pq. But now by this property, I know that the composition of two paths that are beyond the Jacobson subset gives me a path beyond the Jacobson subset, provided they are composable, but that's what we assumed now. So we have really chi pq, and because pq is beyond the Jacobson subset, then this is simply equal to chi pq. Now in the path algebra of EJ, but of course this is chi p times chi q, because if they compose in E, they compose in EJ, of course. And well, remember, by assumption, P is beyond the Jacobson subset and Q is beyond the Jacobson subset, so I can write them as pi of chi P times pi of chi Q. Again, we have established the homomorphism property, and finally, to end with, otherwise, if at least one of the paths P and Q is an element of the Jacobson subset, well, then we can do the following simple computation. We still have that pi of chi p chi q is equal to pi chi pq, because these paths compose. And well, again, remember we have this property from the lemma that well, let me point it to you one more time. Where is it? I had a feeling that I wrote it. Oh yes, you see, we should still remember this property. So a path in the Jacobson subset times anything left or right is a path in the Jacobson subset. So now we assume that at least one of these paths in the Jacobson subset. So this means that this path is necessarily in the Jacobson subset. So this means that pi of this chi pq is equal to 0. And then, of course, this is equal to pi of chi p, pi of chi q, because either pi of chi p is equal to 0 or pi of chi q is equal to 0, or both are equal to 0, right? Because at least one of these paths is in the Jacobson subset. So at least one of these terms is 0, and 0 times anything is 0. So again, we have established the homomorphism property, and this ends the proof of a corollary. I think that this is a very nice corollary, which allows us to see what exactly is the path algebra divided by its Jacobson radical. As we'll see in just a second, this is a general property that if you have a unital algebra and you divide it by its Jacobson radical, then the Jacobson radical of the quotient has the Jacobson radical, the Jacobson radical of the quotient is 0, okay? And well, here we have it from this theorem. Well, you can see that because we removed all edges that are subpaths of the loops, then all paths that you can create by the other edges will not be subpaths of loops. So sorry, will be subpaths of loops. So the Jacobson radical will be 0 of this path algebra. Yeah, it's directly by construction. I mean, by the theorem and by the construction. But if you look at the path algebra of EJ, okay, so that will be proved. This is the beautiful isomorphism of algebras. And here we know by our theorem that the Jacobson radical of KEJ is equal to 0. And here we know that the Jacobson radical of the quotient is equal to 0 because this is the general property of at least unital algebras. Maybe it's generally true, but definitely for unital algebras. And we're going to prove it today. The Jacobson radical of a quotient of an algebra by its Jacobson radical is 0. Okay, let's see a bunch of examples. So for instance, if we take a Kunz graph, if this is my E, then my EJ is just this graph. Okay. I remove, there's only one edge, which is in the Jacobson subset. But this is this edge. So you see, this is why this composition, this presentation of the ideal generated by JE as a linear span, instead of saying that we take a set generated as a linear span, we take a set generated algebraically. So now we have fewer generators, and it's much easier to see what we mean, right? Before we had to write all the paths. There were infinitely many of paths in the Jacobson radical. There were infinitely many paths beyond the Jacobson radical. But now what? We have just two edges, and one edge is in EJ, and one edge is not in EJ, okay? So this means that if I take the KE divided by its Jacobson radical, well, then this will be exactly the path algebra of this graph. So these are just polynomials in one variable. And of course, the Jacobson radical of polynomials is 0. Well, we can take something more complicated. Imagine that, well, for instance, well, how about the Waxman-Soibelman spheres or Hong-Szymański balls? So imagine that we have, say, I'll draw just 3 vertices, but this is a general definition for any number of vertices. We have a vertex, we have a loop at every vertex, a simple loop, a loop of length 1. And then we have an edge going from a vertex with a smaller index to any vertex with a bigger index. So from V1 to V2, from V1 to V3, and from V2 to V3. Okay, so this is, if you take the graph sister algebra of this graph, this will be the sister algebra of a Waxman-Soibelman 5-dimensional quantum sphere. Okay, so if I take it as my E, what will be my EJ? Well, I'll just have a bunch of circles. This will be my EJ. And this will be the commutative algebra. Now, if you want in 3 variables, x, y, z, but now divided by the ideal that tells you that x times y is 0, y times z is 0, and x times z is 0. Okay? So this is a certain commutative algebra, and of course, its Jacobson radical is again 0. But I like the fact that I can somehow see immediately, explicitly, even for a complicated graph, what is the quotient algebra. And dividing an algebra by Jacobson radical is something very popular in algebra. So in the world of path algebras, we can be extremely explicit, and we can enjoy the fact that such a quotient is again a path algebra. Okay, let me do 2 more examples. You can take something like the Kuntz graph ON. So let me take now O3, okay, and say that I take its 2-thing extension. Okay, so this is some funny graph E. So now what is my EJ? Well, this will be the graph of a Kuntz algebra O3, 1, 2, 3. Okay, so this is my EJ. So now this algebra, the path algebra of EJ, is not commutative. In fact, this is the tensor algebra of a 3-dimensional vector space. Okay, because I have 3 loops here. These loops do not commute, right? So this will give me the tensor algebra. And again, this is extremely explicit. Again, the Jacobson radical of the tensor algebra is 0. And well, we know explicitly, even for such a graph, what the quotient is, what kind of path algebra it is. And let me give you one more example. I take a loop, build up out of a number of edges. Okay, so this is my E. And now, clearly, if I remove, yes, sorry. Sorry. In fact, you should have corrected me. I made some mistakes here. This is this one plus 2 vertices. So I have to add the 2-dimensional algebra of functions on a 2-point space. You see, because I do not remove vertices, I only remove edges. Okay, so here, this is my E. So how many vertices I have? 1, 2, 3, 4, 5, 6. So I have 1, 2, 3, 4, 5, 6. So this is my EJ. So here the path algebra of EJ is just K6. So let me make sure that I didn't screw up the previous part. No, I mean, here I keep all these vertices. This is all right. But here I made a mistake, sorry. This vertex remains, so it's a direct sum with K. All right. So that's how it works. And I think this is enough. Do you have any questions concerning this corollary? Nope. Okay, if not, let me back up a little bit and tell you some generalities about the Jacobson radical, which I skipped before and which are very useful. So this is the chaos I apologized for. But I want to prove a lemma, which is then very useful. Well, if you want, this is very much like an exercise someone was supposed to do a week ago, but didn't turn up. There was this exercise that, well, let J be an important, no, what was it? That if you take the quotient of the path algebra by its nilpotent ideal, and it is just the algebra of functions on a finite set, then this when it's and this is the algebra of functions on the set of vertices, then this nilpotent ideal is a Jacobson radical. We had an exercise like this, and yeah, and it didn't even have to be a path algebra. No, sorry. Take an arbitrary unital algebra and take an nilpotent ideal in this algebra and assume that the quotient algebra is just the algebra of functions on a finite set. Then conclude that J is the Jacobson radical of A. There was an exercise like this, but it wasn't done. So instead of doing this exercise, I want to prove for you a more general lemma, namely, I do not assume that the quotient is the commutative algebra of function in a finite set. I assume that this is any algebra and with vanishing Jacobson radical, and that's enough. And obviously, for any function algebra, the Jacobson radical is 0, which I think Majid will show it to us. Okay. So here we start. Let I, so maybe like this, let A be a unital algebra over a field K. And I be an arbitrary ideal of A. Arbitrary. I do not assume that it is nilpotent, okay? Then if I take the Jacobson radical of A divided by I, then this is contained in the Jacobson radical of the quotient. Well, this is one of the things Anya didn't explain to you, I believe, but let's not go back to it. That if you have any ideal, then in an algebra, then the quotient of the ideal is in the algebra. I don't remember. Anya, did you explain it in your presentation or not?
No, I don't.
You didn't. Okay. Anyway, that's really kind of obvious. It's very easy to check that everything is satisfied, but maybe I'll give it as an exercise that prove that if I is a vector subspace of A, then A mod I is an algebra if and only if, I mean, canonically an algebra if and only if I is a two-sided ideal. Yeah, but okay, let's take it for granted right now. And we have this very nice inclusion, which holds for, I repeat, any ideal. I do not assume here that I is nilpotent, okay? Well, let's prove it. Why is the case? I take pi to be the canonical surjection on A mod I. I need some notation.
So I here is arbitrary, yes?
Yes, I is arbitrary, yes. but of course two-sided. Okay, so this is the canonical epimorphism. And
so let me ask why I is contained in Jacobson radical of A?
Well, this is what I'm proving right now. No, I is not contained, but there is an obvious way how you take the quotient. If you take you can divide anything in A by I, and of course you don't need to have that I is contained in the Jacobson radical. It's in general, if you have, let me go to the next page.
Okay, now I understand.
But yeah, you understand, but this is just the question. I have some big ambient vector space V, all right? And inside I have vector subspaces V1 and V2 are vector subspaces in V. I can always take the quotient. Right, I can always define it to be the set, the equivalence class. Well, this is if you want. This is the set. This is V1. Oops. V1 divided by the equivalence relation R, where R is when we say that V is in a relation with W. By definition, if and only if V minus W is in V2. And it makes perfect sense regardless of whether V1, V2 is contained in V1. There's no problem. Well, basically, what happens is that with this definition, we say that V1 over V2 is obviously the same as V1 divided by V1 intersect V2. Okay? So this answers Jacek's question. And that's how I view it in here. And I take this pi to be the canonical surjection, and I take R in the Jacobson radical of A. All right. And then I can draw the following conclusions. I take any y in the quotient. Then, of course, because pi is surjective, there exists an x in A such that pi of x is equal to y. This is just surjectivity. But also, because R is in the Jacobson radical, we know that there exists the inverse of 1 minus xr in A. Okay? Agreed? Now, taking into account that absolutely for any, it doesn't have to be subjective, for any homomorphism say F from A to B unital algebras, we have that one, sorry, let me write it like this. We have, let's say, F of A inverse A is equal to, no, I want to write it down in a better way. F of A inverse F of A. This is, of course, equal to F A inverse A because F is an algebra homomorphism. This is equal to F of 1, but F is a homomorphism of unital algebras. So, in particular, it's not a zero map. As A and B are zero algebras. But then still it is true that F of 1 is equal to 1. Okay. But now you can write it again as F of 1. and write it again, but now this time as f of a inverse, f of a inverse. So we know that f of a inverse is simply f of a inverse outside. Okay, so taking this into account, we infer that for any y in the quotient, algebra A not I, there exists the inverse of 1 minus y pi of r. Well, because 1 minus y pi of r is nothing but pi of 1 minus xr inverse. Okay, so remember, 1 minus xr is invertible because r is in the Jacobson radical of A, but pi of the inverse is the inverse of the pi, so this is why I can have it outside. And now remember that pi is an algebra homomorphism. Pi of 1 is 1, pi of x is y, and pi of r is pi of r. So this is why this is invertible in A, not I, which means that pi of r is in the Jacobson radical of the quotient. Note that thus we have shown that if the Jacobson radical of a quotient is 0, then the Jacobson radical of A is contained in I. Right? And this is a very important implication. Okay, because look, if you what it is that we've done, we proved this inclusion. So if this is equal to 0, then obviously this is equal to 0, and this quotient is equal to 0. Well, if and only if I is contained in the Jacobson radical, or at least the intersection with Jacobson radical is contained. Well, so okay. Yeah, so maybe I should be more precise. This in fact implies that the intersection with the Jacobson radical is 0. No. What am I saying? I know that the quotient is 0. Oh yeah, so it must be contained. I mean, there is no other way. Yeah, this is correct. Okay. If you would have any element in the Jacobson radical of A, which is beyond I, then its class would not be 0. Okay, so I'm sorry, I got confused.
In this frame should be radical Jacobson radical A divided E equals 0. I think it.
Oh yes, thank you, Anya. Of course, yes, of course. Thank you, Anya. Yes, of course, Yep. But now, assume in addition that I is nilpotent. then we know, remember, we proved it some time ago, that any nilpotent ideal is inside the Jacobson radical, so have inclusion the other way around. Then the above implication becomes even nicer. And I'll try not to forget writing 0. This implies that the Jacobson radical of A is actually equal to I. Okay, so that's what you have for nilpotent ideals. If you have any nilpotent ideal of a unital algebra A, and the Jacobson radical of a quotient vanishes, then this means that the Jacobson radical of A is equal to I. And this is sort of the lemma that Majid is going to use today to prove our theorem about the Jacobson radical for acyclic graphs with finitely many vertices, of course. Okay, and now I want to prove the implication the other way around, which is also going to be fun. Well, the opposite implication follows from the general fact, which I told you some time ago, that the Jacobson radical of A by the Jacobson radical of A, I only assume that A is a unital algebra over a field. And this is always 0. Right? So if I is equal to the Jacobson radical of A, then the quotient is A by the Jacobson radical of A, and we know that the Jacobson radical of such a quotient is equal to 0. So indeed, the opposite implication follows, all right? And I say follows because I'm not assuming that the Jacobson radical of A is nilpotent, okay? In fact, I don't know, but I suppose that there might be Jacobson radicals that are not nilpotent. Anya, do you have any information about such a case? Can I have a Jacobson radical which is not nilpotent? I think so, right? What do you think?
I don't know.
but I think this is true. You remember you digged out some properties that something is true if A is Artinian. So
yes,
yeah, so it's I suppose it's related to it. So if your algebra is wild enough, then it might be that the Jacobson radical is not nilpotent. I know that there are some crazy cases, but I think that they are non-unital algebras. That the whole algebra is the Jacobson radical. That A is equal to its Jacobson radical. So if you go wild enough, well, almost anything is possible with the Jacobson radicals. Anyway, so that I'm going to prove this beautiful general fact for arbitrary unital algebras over a field. Okay, I do not assume that the Jacobson radical of A is nilpotent. But of course, the opposite implication immediately follows from this fact. So now let's just prove this fact. Okay, so to prove it, assume that in A, there exists the inverse of 1 minus XR, which is in mod the Jacobson radical. Now pi is again the canonical quotient map, all right? Here I didn't change the notation. So basically, what I just wrote, what I assumed is that pi of R is the Jacobson radical of the quotient. Right, this is because, remember, pi is subjective. So having x running all A, I have pi of x running the whole quotient, right? So then, and then remembering that pi commutes with taking the inverse, which is true for any algebra homomorphism, not necessarily subjective. We see that, in fact, this condition is the condition for pi of R being in the Jacobson radical, okay? So I take an arbitrary element in the Jacobson radical, and I call it pi of R. So I find its representative. R is the representative of the equivalence class that is in the Jacobson radical of the quotient. But then I see that there exists Z in A such that Z times 1 minus XR and 1 minus XR Z is in the set 1 plus the Jacobson radical of A. Agreed? Z is just the inverse. Pi of Z, if you want, is exactly this. This is pi of Z, if you want. Okay. Right. This is an inverse in the quotient. So I can find Z in A such that pi of Z is equal to this inverse. And writing down that pi of Z times pi of this 1 minus XR is equal to 1. That's just the same as writing Z times 1 minus XR or 1 minus XR Z. Remember the two-sided inverse. And if you apply pi to this, it must be equal to 1. So if you lift the pi, it means that these elements belong to the set of the form 1 plus the Jacobson radical of A. All right? And now we are home and dry, because note that all elements of this set are invertible. So you see, if I have an important ideal, I have the same conclusion. 1 plus important ideal is a set of invertible elements. But even if Jacobson radical is not nilpotent, I still know that 1 plus Jacobson radical is a set of invertible elements, because in the definition of a Jacobson radical, I can just take x being equal minus 1, and I've got it, right? However, all elements of the set 1 plus the Jacobson radical of A are invertible, we conclude that, well, if I write Z times 1 minus XR and this inverse, remember, this is an invertible element, so I can take the inverse. So if I write it times Z 1 minus XR, this is of course equal to 1. Well, and I can do the same on the other side, right? I can write it down as 1 minus XR Z times 1 minus XR Z and this inverse. Okay. So you see, because of associativity, if you want, I can put my big parenthesis over here, and I can put my big parenthesis over here, and I can see that 1 minus xr in A. Now, this is important. 1 minus xr in A has a left and the right inverse, but if you have both left and the right inverse, they must be equal. So simply 1 minus xr is invertible. A. Finally, note that as x is arbitrary, that's what we assumed. We conclude that R is in the Jacobson radical of A. So pi of R is equal to 0. Which ends the proof, because I took an arbitrary element in the Jacobson radical of the quotient, and I proved that it is equal to 0. Hence, the Jacobson radical of A, no, the Jacobson radical of A is equal to 0. And this is a very useful property to bear in mind. Okay, let's see how much longer we are going to be radical. We have only 8 minutes left. Well, let me now write the conclusion, because this is a beautiful lemma. So summarizing, we have proved the following lemma. That I be a nilpotent ideal in a unital algebra over a field A. Then we have the following equivalence. I is the Jacobson radical of A, if and only if the Jacobson radical of the quotient algebra is equal to 0. Okay. And this is much better than saying that the quotient algebra is say, some function algebra on a finite set. Okay. This is far more general. All that we need is that the Jacobson radical of a quotient vanishes. It need not be the function algebra, or it need not be a function algebra, and it need not even be commutative. It can be, for instance, the Kunz algebra. I mean, sorry, the tensor algebra, not the Kunz algebra. When I see a graph, I immediately think about the graph sister algebra, but here we are still in the realm of path algebras. So when I take the Hawaiian E-ring graph, then it will be the tensor algebra, not the Kunz algebra. Okay, so that's a very, very nice lemma, and this lemma allows us to prove the following proposition, which will be proven by Majid in the recitation class. So I'm only going to write it, but not prove it. Okay, so let E be an acyclic graph. So no loops. And with finitely many vertices. Then the Jacobson radical of its path algebra is in fact the arrow ideal. And Majid will prove it today after the break, okay? Because basically, then what you have to do is to prove that in the acyclic graph, the arrow ideal is nilpotent. And then when you take the quotient, well, then this is the commutative algebra of functions on in zero, which has the Jacobson radical equal to 0. So by the lemma we just proved we are done, okay? But let's leave it to the recitation class. Okay, and now I think this ends our radical behavior. Now we can go back to simplicity and clean up the other part of the lecture. So have you got any radical questions, please? Nope? No radical questions? Well, we have 4 minutes left, so let's see how much I'm going to do. But anyway, we have cleaned up the radical part. That's done. I have no more to say. Well, there will be some exercises concerning, well, at least one exercise, no, maybe more, concerning the radicals, but nothing more in the lecture. Okay, I'm going back to the issue of simplicity. Okay, I have 3 minutes, maybe I can still face it. So Sophie will show us today that if A is a finite dimensional Caesar algebra, then it is of the form, when it is necessarily unital, and it is of the form the direct sum over some finite set of full matrix algebras, so M and C, where I is a finite set and I is a non-zero natural number for all I in I. Okay, so Sophie will show it today in the recitation class. But this allows me to draw the following beautiful corollary, and I'm wondering what to do because I will need 15 minutes to prove it. Yeah, okay. Okay, I guess I will steal 15 minutes from the recitation test because I want to do this corollary and finally be over and done with. Okay, so this allows me to prove the following corollary. Yeah, I apologize for the timing of our classes to fluctuate, but this is very important that you make a break at a certain point at which it is reasonable to do so. Okay, it's very hard to finish in the middle of a sentence and then pick it up in a week, or as it is in this case, in 2 weeks. Which reminds me of a very beautiful story narrated to me by Paul Baum once upon a time, that he was discussing, and it was possibly with Novikov, from the Novikov conjecture, some issues concerning the proof of the famous Atiyah-Zinger index theorem. And Novikov claimed, no. If you have a proof of Singer index theorem, you have to use such and such fact. And Paul said, no, it's not true. I don't have to use this fact to prove the Singer index theorem. Okay, they disagreed. And 5 years later, they incidentally bumped into each other. And then Novikov, without saying hello or good morning or how are you, he just immediately said to Paul, yes, you're right. You don't need this fact to prove the Singer index theorem. And it was, 5 years in between. So anyway, that's not very user-friendly, so I'm not going to do it. So let me steal these 15 minutes and not only phrase, but also prove this corollary. And then it will be in line with Sophie's proof today concerning the form of finite dimensional sister algebras. So let A be a finite dimensional sister algebra. And don't worry if you don't know what the sister algebra is, because by what Sophie will show you, this is just a finite direct sum of full matrix algebras. Okay. So let A be a finite dimensional sister algebra, and let E be a graph. Then the sister algebra A and the path algebra CE are isomorphic as unital algebras. So in particular, I don't care about the star structure. Apply the forgetful functor. And a unital star algebra is in particular a unital algebra. Of course, over the field C of complex numbers, because this is a sister algebra after all. So these two algebras are isomorphic as unital algebras. If and only if the set of vertices is finite, of course, otherwise the path algebra would not be unital. But, and this is important, the set of edges is empty. Okay? And both these algebras are isomorphic to the function algebra. All functions on E0. Okay. Well, in fact, something more general is true. The Jacobson radical of any sister algebra is 0, and the Jacobson radical of any non-commutative path algebra is non-zero. Sorry. So forget the Jacobson radical. No, I take it back. Sorry. I'm confused. And I think you can prove a more general statement. You can go beyond finite dimension, but I don't want to do it here for a good pedagogical reason. Namely, I mean, we can forget the star structure. It's just an additional algebraic structure. We can just skip it. But when we go into the infinite dimension, then you see every sister algebra must be a Banach space, and it's automatic only for finite dimensional vector spaces, but they are norm complete. Okay, So any finite dimensional vector space is a Banach space, and you don't have to take any completion. Typically, if you have an infinite dimensional vector space which is normed, in order to make it a Banach space, you have to norm complete it. And this is why I don't want to compare infinite dimensional path algebras over complex numbers with infinite dimensional sister algebras, because when it's not just a question of the existence of a star structure on the path algebra, it's also a question of completion. And basically, you know, this construction of a path algebra is completely algebraic. There's absolutely no reason for the path algebra, the infinite dimensional path algebra, to be norm complete, whatever reasonable Banach norm you can put on it. Okay, so that's why I think that here this comparison is very clean and straightforward. In the finite dimensional case, it's purely algebraic. There are no norm completions, and we can draw this corollary from our rigidity theorem. Right? Remember that we proved that if a path algebra has a direct sum and subalgebra, then this direct sum and subalgebra has to be isomorphic to the path algebra of a subgraph. And then we also realized that the path algebra of a subgraph is never simple when it is non-commutative. If it's non-commutative, then it's not simple. So therefore, it can never be a matrix algebra. It can never be a non-commutative matrix algebra. So that's exactly what we are going to use. All right. So let's now prove this corollary.
I have a question about the formulation of this corollary.
Yes.
Do we really want two-sided implications, not just one-sided? I mean, if E0 is finite and E1 is empty, then A and CE does not necessarily be isomorphic, I think.
Well, if E0 is finite and E1 is empty, then the path algebra is just this function algebra, and of course it is a finite dimensional sister algebra.
Yes, but in this formulation, we start with some A, some finite dimensional sister algebra A, and some graph. And it can happen that both are isomorphic to maps from finite set to C, but say maps with different from different sets with different cardinality.
Yes, you're right. Yes, you're right. You're right. This is badly formulated. Thank you, Jacek. Yes, you're absolutely right. You're absolutely right. Yeah, maybe let me do it this way. I erase it. And just write implication. Okay, because if I have that the path algebra CE is isomorphic to a sister algebra, then it can happen only when to a unital sister algebra. Then it can happen only when E0 is finite and E1 is empty. So one part is obvious. It is, if it is isomorphic to a unital algebra, it is a unital algebra, so E0 is finite, so that much we know. But we now know more. If it is to be isomorphic to a unital, to a finite dimensional sister algebra, then in fact also E1 has to be empty. Okay, yeah, okay, thanks. And the other way around, I mean, it's not, what I really meant is completely trivial. If I do have these two conditions satisfied, then my path algebra is obviously a commutative sister algebra. Okay, so maybe you can phrase it in a better way later on, but for the time being, let me prove this one. That's the core. Thank you, Jacek. Okay. So if Yeah, and I have it it's written the first way. Maybe I should I will write it this way. Also, if E0 is finite and E1 is empty, then CE is a finite dimensional unital system algebra. Now with this sentence can be put at the end. I wanted both implications, but you're right, Jacek. I cannot phrase it in some simple if and only. Okay. So for starters, I prove this obvious implication. So if E0 is finite, yes, and E1 is empty, then algebra CE is just function algebra on E0, but you can write it down as the sum over V in E0 of 1-by-1 matrix algebras. Okay. And I know now that this is by what Sophie will show. I know that this is as an algebra, as a unital algebra, this is a finite dimensional system algebra. Okay. So this way it's completely obvious. And now vice versa. If A is a finite dimensional algebra and A is isomorphic to CE as a unital algebra, well, then of course FPE is finite. So E1 contains no loops. Well, there is a theorem that we proved a long time ago, which basically said that if E is a finite graph, then FP is finite if and only if this graph is acyclic. Okay. And well, since FP is finite, obviously E0 and E1 is finite, so it is a finite graph. So it satisfies the preamble of this theorem, and its finiteness of P means that the graph is acyclic. So in particular, no edge is a loop. Okay. Now, suppose that the set of edges is non-empty. then the path algebra CE is non-commutative because, well, if I take an edge which is not a loop, we have the following. We have that chi S of E, chi of E is of course equal to chi of E, which is non-zero element because it's part of a basis. And on the other hand, 0 is equal to chi of E times chi S of E. Right, the end of the edge E, because E is not a loop, cannot be its beginning. So this is 0. So this proves non-commutativity of C of E if the graph E has at least one edge that is not a loop. Okay. So hence, this isomorphism implies that there exists an index I such that Ni is bigger than 1. Otherwise, our sister algebra, remember, which is isomorphic to the direct sum of full matrix algebras, finite dimensional full matrix algebras. So at least one of these matrix algebras has to be non-commutative. Okay, so there is at least one index I such that Ni is strictly bigger than 1. Okay. But then M and I is isomorphic. Oops. To a direct sum on subalgebra of CE which is impossible because M and J of C is simple, as we have seen in the recitation class, and no non-commutative algebra is simple. Right, if it is non-commutative, it has a non-trivial arrow ideal, and then you have non-trivial commutative part, so that's definitely not a simple algebra, so that's impossible. Okay, so this way we have a desired contradiction, and we can conclude that E1 is the empty set as needed. Okay, and this proves the theorem. And let's now make a 10-minute break and resume at 11:30. Okay, thank you very much. I stop recording.